Welcome to the second session of the differentiation series. In this session, we will continue to introduce the differentiation rules such as the product and quotient rules. We will also introduce the Squeeze Theorem as well as how to use it to evaluate two important limits. We will also demonstrate 8 worked examples in this session.
Hello, Math Champions! I'm Dr. Chen. If you want to improve your math skills and understanding so that you gain confidence, enjoy math more, and get better results, click subscribe and hit the notification button so that you don't miss anything.
Welcome to the series of differentiation, and this is the second session of this series. Now we are going to introduce the product rule. The product of two differentiable functions f and g is itself differentiable. The derivative of f of g is the derivative of the first function times the second, plus the first function times the derivative of the second. The first principle is adopted here to prove this rule, which involves a step of subtracting and adding the same quantity, which is shown in red here. Therefore, the derivative of f of g equals the limit of f of x plus delta x times the fraction of g of x plus delta x minus g of x all over delta x plus gx times the fraction of f of x plus delta x times f of x all over delta x as delta x approaches 0. According to the sum and difference rules as well as the multiplication rule, the derivative of f of g equals the limit of f of x plus delta x as delta x approaches 0 times the limit of g of x plus delta x minus g of x all over delta x as delta x approaches 0 plus the limit of g of x as delta x approaches 0 times the limit of f of x plus delta x minus f of x all over delta x as delta x approaches 0, which is the derivative of f of x times g of x plus f of x times the derivative of g of x. Please note, the limit of f of x plus delta x equals f of x as delta x approaches 0 because f is given to be differentiable and therefore is continuous. Here, example 1 is to find the derivative function of f of x, which equals x squared multiplies by square root of 1 minus x squared. We start by rewriting the function f of x to x squared times 1 minus x squared, or in parentheses to the power of 1 over 2. According to the product rule we just learned, the derivative function equals x squared times the derivative of 1 minus x squared, or in parentheses to the power of 1 over 2, plus 1 minus x squared, or in parentheses to the power of 1 over 2 times the derivative of x squared, which can be further simplified by factorizing and combining the like terms. Finally, the derivative function f prime of x equals x times 2 minus 3x squared, or in parentheses divided by the square root of 1 minus x squared. Example 2 is to find the derivative of the function, which is x squared times the cubic root of x squared plus 2x. According to the product rule, as well as the chain rule we just learned, its derivative equals the derivative of x squared times x squared plus 2x, or in parentheses to the 1/3, plus x squared times the derivative of x squared plus 2x, or in parentheses to the 1/3, which is simplified to 2x times x squared plus 2x to the 1/3 plus x squared over 3, or times x squared plus 2x, or in parentheses to the negative 2/3 times 2x plus 2, or in parentheses as shown on the screen. After taking out the common factor x squared plus 2x, or in parentheses to the negative 2/3, the remaining part can be further simplified. Finally, the derivative of the function equals 2x squared times 4x plus 7, or in parentheses times x squared plus 2x, or in parentheses to the negative 2/3. Example 3 is to find the derivative of f of x, which equals 3x minus 2x squared, or in parentheses times 5 plus 4x, or in parentheses. We still apply the product rule to find its derivative here. So f prime of x equals the derivative of 3x minus 2x squared, or in parentheses times 5 plus 4x, or in parentheses plus 3x minus 2x squared, or in parentheses times the derivative of 5 plus 4x, or in parentheses. This expression can be simplified to 3 minus 4x, or in parentheses times 5 plus 4x, or in parentheses plus 3x minus 2x squared, or in parentheses times 4. Then the expression can be expanded and simplified to combine the like terms. Hence the derivative of f of x equals 15 plus 4x minus 24x squared. Now we're going to briefly introduce the quotient rule. The quotient of f of x over g of x of two differentiable functions f and g is itself differentiable at all values of x for which gx does not equal 0. As it can be seen on the screen, the derivative of f of x over g of x is given by the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator, or divided by the square of the denominator. Now let's try to prove the quotient rule. Now we're going to prove the quotient rule here. The derivative of f of x over g of x. The condition is both f of x and g of x are differentiable at all values of x, and gx does not equal 0. The proof is also based on the first principle. As we can see, the derivative of f over g equals the limit of f of x plus delta x over g of x plus delta x minus f over g, or divided by delta x as delta x approaches 0. After simplifying the expression, we subtract and add the same quantity of f of x, g of x as shown in red color here. Hence the expression is simplified to g of x times the limit of f of x plus delta x minus f of x all over delta x as delta x approaches 0 minus f of x times the limit of g of x plus delta x minus gx all over delta x as delta x approaches 0 divided by the limit of g of x times g of x plus delta x as delta x approaches 0. Hence we have proved the quotient rule. It states that the derivative of f of x over g of x is given by the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator, or divided by the square of the denominator. Example 4 is to find the derivative of f of x, which equals x squared minus 2, all over the sum of x and 3. Here we may apply the quotient rule to find its derivative directly. However, as an alternative, we may transform this function and then apply the power rule to find its derivative. So the numerator x squared minus 2 can be transformed to x squared minus 9 plus 7. Hence, f of x equals x minus 3 plus 7 times x plus 3, or in parentheses to the negative 1. Accordingly, its derivative f prime of x equals 1 minus 7 over x plus 3, or in parentheses squared. Example 5 is to find the derivative of f of x, which equals 5x minus 2, or over the sum of x squared and 1. Now we apply the quotient rule to find its derivative of this function, which equals the derivative of 5x minus 2 times x squared plus 1, or in parentheses minus open bracket 5x minus 2 close bracket times the derivative of x squared plus 1, or over x squared plus 1, or in parentheses squared. After working out the derivative of 5x minus 2 as well as x squared plus 1, the derivative of the function equals 5 times x squared plus 1, or in parentheses minus 5x minus 2, or in parentheses times 2x, or over x squared plus 1, or in parentheses squared. After being further simplified, we find its derivative, which equals negative 5x squared plus 4x plus 5, or over x squared plus 1, or in parentheses squared. Example 6 is to find the derivative of f of x, then simplify it, given that f of x equals x over the cubic root of x squared plus 4. So its derivative equals x squared plus 4 to the 1/3 minus x times 1/3 times x squared plus 4, or in parentheses to the negative 2/3 times 2x, or over x squared plus 4, or in parentheses to the 2/3. After taking out the common factor, it is simplified to x squared plus 12, or over 3x squared plus 4, or in parentheses to the 4/3. Example 7 is to find an equation of the tangent line to the function f of x at the point of -1 and 1. The function f of x equals 3 minus the reciprocal of x, or over the sum of x and 5. First, we need to find the derivative function using the quotient rule, and then substitute x by -1 to find the gradient at this point, so that we may find the line equation. Since f of x can be rewritten to 3x minus 1, or over the sum of x squared plus 5x, then f prime of x equals the derivative of 3x minus 1 times x squared plus 5x, or in parentheses minus 3x minus 1, or in parentheses times the derivative of x squared plus 5x, or over x squared plus 5x, or in parentheses squared. After working out the derivatives, expanding and the brackets, and the combining the like terms, f prime of x is simplified to negative 3x squared plus 2x plus 5, or over x squared plus 5x, or in parentheses squared. Accordingly, we calculate f prime of 1, which equals 0. Hence, the equation of the tangent line is that y equals 1. The squeeze theorem concerns the limit of a function that is squeezed or sandwiched between two other functions, each of which has the same limit at a given x value. The theorem states that if h of x is less than f of x, which is also less than g of x for all x in an open interval containing c, except the possibility at c itself, if the limit of h of x as x approaches c equals the limit of g of x as x approaches c, which equals a constant L, then the limit of f of x as x approaches c exists, and it equals L. We are not going to prove the theorem here, but we will use this theorem to prove the following two special trigonometry limits. Example 8 is to prove these two trigonometry limits using the Squeeze Theorem. The first one is the limit of sine x over x as x approaches 0 equals 1. The proof is based on the unit circle with an acute positive angle theta, which is measured in radians as seen in the diagram. The coordinates at point A, P, and Q are 1 tangent theta, cosine theta, sine theta, and 1, 0 respectively. Hence, it is not difficult to find that a circular sector OPQ is squeezed between the triangle OPQ and the triangle OAQ. Accordingly, the area of triangle OPQ equals sine over 2, the area of triangle OAQ equals tangent theta over 2, while the area of the sector OPQ equals theta over 2, which is sandwiched by the area of triangle OPQ and the area of triangle OAQ. Here we continue to prove the two trigonometry limits according to diagram, as well as the relations among the areas of two triangles and a sector. We have the inequalities of sine theta is less than theta, which is less than tangent theta. After being divided by sine theta, the inequalities become cosine theta is less than sine theta on theta, which is less than 1 over cosine theta. Since the limit of cosine theta equals 1 as theta approaches 0, hence, according to the Squeeze Theorem, we have proved that the limit of sine x over x equals 1 as x approaches 0. Now the second question is to prove the limit of 1 minus cosine x all over x equals 1, based on the double angle formula. The numerator of the limit 1 minus cosine x is written to 2 square of sine x over 2. Hence the limit is simplified to the limit of x over 2 times the square of sine x over 2 over x on 2, or in parentheses squared as x approaches 0, which is further simplified to the limit of x over 2 as x approaches 0 times the limit of open bracket x over 2 over x on 2 close bracket squared as x approaches 0. Since we have known that the limit of x over 2 over x on 2 equals 1 as x approaches 0, the second limit equals 0 times 1, which is 0. If you enjoyed this video, please give it a thumbs up and subscribe to help me make more math content like this. I will see you in the next video.